Hello everyone, my name is Guilherme and I'm here today with Mateus Basso to show the use of machine learning for image classification, a geological application. And our co-workers here is João Souza, Ramin and Alexandre Vidal. So the summary here that we show, it's the use of machine learning as a tool in geosciences, the method that we are using here, that is the convolutional neural network, and the two study cases. The first one presented by me, the second one presented by Mateus Basso. So, the machine learning is an interdisciplinary tool that's used in several fields of sciences, for example, the biology, chemistry, medicine, among others. And in geological application, we have, for example, here the use in remote sensing, in the seismic data, and the identification of sedimentological process, the electrophysics definition, among others. So it's very useful for geosciences also. So what is the convolutional neural networks? Well, it's a technique that's used in the field of the computer vision. So it's very useful for image classification, object detection, segmentation of the image and face recognitions and all of applications. And for example, it's very useful for self-driving cars, for example. So the main idea here, for the training, you need to provide an image with the previous classified or not. But the main idea is the idea to get some kind of classification for this. And we have a lot of types of convolution inside of this image. By the end, we have an output for the identification of the image or object detection and etc. So, the first study case here is the use of machine learning methods for dissolution features classification in acoustic borehole images. And why we need to use the machine learning in this case? Why it's very useful? Well, the first thing is that it's possible to work as fast and an efficient preliminary classification in image logs. It's very time consuming when we are working with, for example, a large number of wells and thousands of meters of logged intervals to classify. And also it's very useful, for example, we have a class standardization for entire field. So, what to expect using this method? Here we are working with carbonated deposits of the Barra Velha Formation. So the main idea is the identification of the main zones with occurrence of the dissolution and how the intensity of dissolution occurs in each well in our work area and in the zone of the reservoirs, for example, Barra Velha 300, 200 and 100, and the lateral correlation with other wells and of course also using seismic data. So what's our first approach here that we have here? We are working with Halliburton Cast 2 and we choose one well that can be integrated as a result with other special wells, for example, mineral inversion provided by Jan 2, and also we have NMR for Emeril, and we have for this well also basic petrophysics from plugs and lateral samples, and also we have the well core for comparison of the results. So we have a lot of that data integration here. Well, and how it works here, we have to export the image log, of course, the image of the well, and splitting a slice of 10 centimeters in the vertical at a 1 to 10 scale. And this was chosen because we have the same log resolution of other tools, each 10 centimeters. And we have to do here some quality control to remove images that have a bad quality, for example, breakouts, lateral plug samples, strong tool markers, etc. And also we have here proposed a number of classes to our dissolution intensity for classification and training. So this is the main idea of the model training. We have the image extracted from the borehole acoustic imaging, and we're using here the MobileNet V3 as a feature extractor, and by the end we have a classifier. So what we have acquired using this method? We are using here 6 classes that varies from non-VUG to well-developed dissolution or CARS. And we have, for example, the VUG matrix dissolution or VUG fracture dissolution, and that varies according to intensity, and this will reflect in different types of image and testers in the images, as we can see here in the left. And in the right, we have 2 examples here. One is scale 1 to 30, how the proposed classification that we have done in the track 2 and the classification provided by the machine. And in the general overview for the scale 1 to 100, we can see that we have a good match between both classification provided by us and the classification provided by the machine. So, the dataset was formed by 1,871 images, and we have a train set with 1,496 sections and test with 375 sections. And we have here for the 6 class classification overall accuracy of 0.75. So, what's our limitations, improvements, and next steps? Some limitations could be correlated with scale of observation of some classes, because, for example, we have faults with high angle could be not represented in images of 10 centimeters. Also, we have some kind of similarity of some features, for example, bedding dissolution or even fractures, so how to classify it. Also, quality of images, because when we're working with directional wells, we have a lot of Mark IIs that could be very hard to work. And also different type of tools, for example, Halliburton, Baker, Schlumberger, different types of acquisition image qualities, and also different types of the drilling mud, oil-based versus water-based, so this will reflect in our quality also. So this is something that we need to take in mind when working with these methods. Well, for next steps, we're still working with these Halliburton tools that we are working now, and test in other scales, test in other wells, and try to improve this accuracy of the machine. Okay, thank you. The next presentation now will be presented by Mateus. Thank you.
Okay, hello everyone. My name is Mateus Basso. I'm a geologist and researcher at CEPETRO Unicamp, and I've been working together with Guilherme in this study about machine learning applications for image classification. And I would like to continue this presentation talking about the second study case that Guilherme mentioned, which is machine learning approaches for petrographic image analysis. So why should you use machine learning methods for petrographic image analysis and rock classification? There are a few good reasons for that. For example, this type of study may work as a fast and efficient preliminary classification. So of course the idea is not to replace highly detailed petrography, but rather to be able to create a classified database that could be readily available for use. So we started this project very recently, and the first idea is to perform facies classification considering the entire thin section high resolution scan images, where we could apply and test different classification schemes. Also make tests with plane and crossed polarized thin section images, and also apply different methods and approaches of machine learning. About our database, we have been using 370 thin section scans images of 3 wells from the Santos Basin. And the idea is to add more 300 thin sections until the end of the year. And there are more to come, so the idea is to create a database of at least 1,000 thin sections for this work. About classification scheme, we have been using for the project in general as a standard the Gomes and others 2020 classification for the Barra Velha Formation carbonates that's represented in this image here in the left. And as you can see, this is a very interesting and complete classification, but it has many different classes. And as the authors themselves suggest, those classes can be upscaled from a highly complete classification to another considering only the end members. So having that in mind, we have performed the classification of our 370 thin sections based on 3 different classifications. A simplified one with 5 classes, an intermediate with 9, and a complete classification with 23 classes. All of those based on Gomes and others 2020. And you can see the result of this classification process in this image here in the right, where we have this facies upscaling from a complete classification to a simplified one. And we can readily see the first challenge with this database, which is the non-uniform data distribution, as our database is dominated by greenstone samples. But we expect that this effect should be attenuated as we add more thin sections to this database. About our computational models, we have tested for now 2 different models. They follow a similar strategy. They're both of them basically mix convolutional neural networks and multilayer perceptron. And also both methods, it was necessary to perform this data conditioning step where the images were downsized for the sake of computational time and also automatically cropped. This first model is based on the MobileNet third version that basically leverages the thin section images through the convolutional layers to extract a vector that basically summarizes the thin section content. Those vectors are then concatenated and classified. The second model is quite similar but is inspired in the architecture VGG19. So we have the conditioned thin sections going through the convolutional layers followed by a max pooling layer. Then the outputs is merged and classified using softmax. As some preliminary results of this work, we have performed some tests for the 5-class classification, and the first model presented an accuracy of 89% and the second one of 82.8%. So those are promising numbers, but you must keep in mind that this is only for the simplest classification scheme, and also that those numbers might be affected by that data distribution, as we saw that the database is dominated by greenstone samples. So as next steps, we want to keep comparing different architectures, analyze the confusion matrix to assess where the errors are being made, and also study the effect of number of layers, depth of the model, and input size to get to the optimum model. Okay. So I would like to acknowledge and thanks all of our partners, and also thank you for the attention so far. Thank you. Bye bye.